Hi everyone, myself Navyatha working as Assistant Professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today I am going to discuss about the topic reasoning about functional dependencies. The overview of my presentation includes, so what are the Armstrong axioms, which are also known as inference rules, and how to find the closure of a set of attributes. So before going to deal with these two topics, in our previous video we have already discussed about what is a functional dependency. What is an FD or functional dependency? So, if one column of a table derives another column uniquely, then we can say that one particular column derives the another particular column. That is what? Let us discuss here with a simple example. X tends to Y, whether it is a FD or not. If at all X derives Y uniquely, then we can say that it is a Y is functionally dependent on X. Here X is called determinant, Y is called dependent. This is dependent and this is determinant. Why? Because this X uniquely derives Y. What are these X and Y? These are nothing but the columns, whatever the attributes that are there in a particular table. For example, X is SID and Y is S name, student ID, student name. Here SID derives S name uniquely. Then we can say that it is a valid functional dependency. Valid F, that we have already discussed the types of FDs in our previous sessions. Now let us discuss some of the rules to validate these FDs and how to find the closure of a set of attributes. So let us consider what are Armstrong axioms or inference rules. So what are the rules here? Rules are nothing but which have already been proven. That means if at all we are following means, that means what? Those are very good and those are already proven. Then only we can able to follow some kind of rules. So here also let us discuss here inference rules which will be there in our mathematical foundations of computer science or else discrete mathematics. Right. So some statements, if at all we are dealing with some statements or else premises. For example, let us P as a premise or a statement, right? So, I love chocolates. This is my statement, right? Next, P implies Q. That means what? If then conditional statement. Implication means what here? If then implication, right? So, what is P implies Q? If I love chocolates, then I love ice cream. If I love chocolates, then I love ice cream. That is what the conditional statement. Here P is what? I love chocolates. So here P implies Q. So what is P here? I love chocolates. If I love chocolates, then I love ice cream. That means Q is what here? I love ice cream. This is what Q and this is what here P. With this two set of premises or else with this two set of statements, we can conclude one conclusion. Therefore, if I love chocolates and the second statement is if I love chocolates, then I love ice cream. So, from these two set of statements, I can conclude, therefore, I love ice cream. I love ice cream. That is what here I love ice cream. This is what exclusively clue. So, from these two set of statements, P implies Q, I can conclude Q. How I can able to write this representation? See, if I used to combine these two, then I will get this conclusion. So, P and P implies Q derives Q. That is what the solution. This is one of the rules which is always be a tautology, which is always been proven. Let us, how we can able to know this one as a tautology or else it is correct, valid statement, valid inference, valid statement, how we can able to justify that one. Let us consider truth table for this one. So, what is the truth table here? What is the truth table? How many variables are there here? We have PQ, two variables, right? So, let us consider these two tables, P, Q, Next, P implies Q. Next, P and P implies Q. Next, what is the last one? P and P implies Q implies Q. Right. So, let us consider the truth table for this one. As we have two different variables, right? So, 2 power n, that is what the formula. 2 power n, where n represents number of variables. That means 2 power 2, 4 combinations we will get, right? True, 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 false, false, true and false, false. Next, what is implication? If P, then Q, right? Implies. So, if at all P is true and Q is false, then only P implies Q will be false. That is what the resultant statement of this one, implication. If at all P must be true, Q must be false, then the resultant statement must be false. So, let us deal this one. So, that means P is true, Q is false, then only false. Rest of all will be true. This is what P implies Q. Next, we used to imply the conjunction of between P and P implies Q. So, what is P here? P and only these two columns we have to consider. P and P implies Q. So, here this will be true. What is conjunction here? Conjunction means if at all both the statements are true, then only the resultant will be true. Rest of all will be false. So, here these are the two statements are true, then only the resultant will be true. So, if any one of the case fails, then it will be false. This also will be false. This also will be false. That is what between the conjunction between these two, P and P implies Q. Now, let us see for these columns, P and P implies Q. Consider this as P and this is single as Q. Now, it is in the form of what? P implies Q, right? So, this one as P and this one as Q. Now, we have to check P implies Q. The statement, if what is P implies Q? If P is true, Q is false, then the resultant statement must be false. That is what the shortcut, right? So, here, so this is what true. Why? Because true and true. And here also true. Here also true. Here also true. What we got here? It is a tautology. So, this statement is a valid statement. So, these are some of the rules, modus ponens, modus tollens, which are already proven, and these are all valid statements. In this way, we can give the justification by considering the truth tables and everything, and by the statements also. Just now I have already explained the example. P statement, I love chocolates. P implies Q. P implies Q means what here? If I love chocolates, then I love ice cream. Therefore, from these two statements, I can conclude a conclusion, I love ice cream. So, to justify that statement is I have represented this truth table in the form of truth table. And it is always true. Why? Because we got tautology here. Why I am representing all these things? Because here we are using some rules which are already proven as true. Right? Why we have to use these some Armstrong axioms? To find out the closure set. What is a closure? Everything we'll discuss in the next slide very briefly. Right? So, here what are the Armstrong axioms or else rules? So, here the term Armstrong axioms refers to the sound and complete set of inference rules. These are some set of inference rules or axioms introduced by whom? Introduced by William W. Armstrong. That is used to, for what purpose? Used to test logical implication of functional dependencies. That is nothing but what are the functional dependencies, how we can able to derive some set of functional dependencies, whether they are correct or incorrect, how we can able to derive. So, by using these rules, we can able to derive some of the functional dependencies. Next, Armstrong axioms are used to conclude functional dependencies on a relational database. So, here let us discuss these things. And some of the rules, Armstrong, what are the inference rules that we use to define functional dependencies, that we will see now. So, these are some of the rules, axioms, Armstrong axioms rules or inference rules to define functional dependencies. And here we use ABC to denote sets of attributes over a relation schema. That means, if at all there is a schema, that is nothing but a table representation, and here A, B, C are nothing but different columns or else attributes. So with these attributes, let us define what are the rules here. So what is reflexivity? If B is subset of A, then A tends to B. A derives B here. So what is this? This is nothing but a functional dependency. A derives B. That means what? Here A can uniquely identify B. In the same manner, what is augmentation rule represents? What is, if A tends to B or else A derives B, then AC derives BC for any arbitrary constant C. For example, SID tends to S name or else SID derives S name. SID derives S name. So this is what A, this is what B. If A derives B, I'm explaining this step. If A derives B, then AC derives BC. That means SID comma S mobile number derives S name comma S mobile number. This is what AC and this is what BC. Just I have added this more column. If at all A derives B, then we can say that AC derives BC for any C. Right. So next, what is transitivity? If A derives B and B derives C, then we can say that A derives C. This is what transitivity. What is union operation? A derives B and A derives C, then we can derive A derives BC. We can unite these two. Why? Because see here, a single column is deriving uniquely one column and the same column is deriving uniquely this column. So we can combine the right side things. What? Determinants or dependents? Dependents. We can combine the dependents BC. That is what union. Next, decomposition. So A derives BC, then we used to split. Decompose means we used to split. So if at all A derives BC, then we can split it as A derives B and A derives C. A derives B and A derives C. So here let us take one more example. AB derives C. AB derives C. So whether we can split this one as A derives C and B derives C by using decomposition rule? By using this decomposition rule, can I able to decompose like this? No. Why? Because here AB combinedly they used to derive this column uniquely. Only by combining AB only we can derive C uniquely. That is what the statement FD is meant for. So if I decompose this FD into these two statements, then the meaning at all will be changed. What is that one? Here, if at all I used to decompose, what I am supposed to deliver here? Single A uniquely derives C and B uniquely derives C. That is not the thing here. Here, what is the FD here? AB combinedly derives C. That is what my intention. So, in this way, we cannot decompose. Okay. Next, pseudo-transitivity. If A tends to B and CB tends to D, then AC tends to D. So, here these three A, B, C and D are nothing but different types of columns or else the attributes in a particular table. So, these are some of the axiom rules. By using these rules, so let us define how to find closure, right? So, we can compute the closure of a given set F of FDs by applying the above rules. We can find out the closure of particular FD, right? So, how we can find out this closure? What is the definition? The set of all FDs implied by a given set F of FDs is called closure, which is denoted as F plus. Rather than explaining with the definition, you will better understand by explaining with a simple example. So, what is that example? Let us discuss. For example, before going to that example, let us discuss these two steps. How to find closure. Step 1. Add the attributes contained in the attribute set for which closure is being calculated to the result. That means whatever the closure that we are going to calculate, first of all, we need to add all the attributes given in the FD. Then, we need to recursively add the attributes to the result which can be functionally determined from the attributes already contained in the resultant set. So, it will be better understood by representing with a simple example. See here, This is the relation given, right? Next, these are the functional dependencies. F. These are the already given functional dependencies. And we need to find the closure of this one. We need to find the closure which is represented by F plus, which is represented by F plus, right? So, whatever this F plus, this is nothing but what we called as closure. How we can find this closure? By including all the FDs given, already given. So, this F plus contains A implies B, right? Next, A implies C, CG implies H, CG implies I, comma, B implies H. By including all the FDs, first of all, we need to find a closure. Later on, from these FDs, we can derive some more FDs. Like, for example, A derives B, A derives C. By union operation, what A can derive BC, right? By union axiom rule, which we have discussed previous slide, right? So, from the given set of FDs, we can able to derive some more FDs. See here, from A derives H is obtained. A derives H is obtained by considering these two. Why? So, here A derives H is obtained by considering transitivity. What is the transitivity? A derives B and B derives H. So, it's just like transitivity. A derives B, B derives C. Then A derives C. This is what our transitivity rule, right? In Armstrong axioms or in inference rules. So, instead of C, here they have given H. That is a simple thing. So, here I have included A derives H, and at the same time, here one more FD, CG derives HI. How I can obtain this one? CD derives HI. CD derives HI. How I can obtain? From these two FDs. So, here this is one and this is one, right? Same columns derives two different columns. So, we can able to combine those two by union. So, by union operation, we can able to derive CG derives HI. So, here I have included these two. Next, AG derives H. How I got this functional dependency? By pseudo transitivity. So, A tends to C and CG tends to H. Next, AG derives I. How I got this functional dependency? By considering pseudo transitivity. A tends to C and CG tends to I. Here I have missed one more. What is that one? From these two. What is that one? A tends to B, A tends to C. Then we can derive A tends to BC by union. This one also can be included. A tends to BC. This one also can be included in closure. Okay. So, hope you understand. How to find the closure? Initially, we will give some set of functional dependencies. These are the some set of functional dependencies. We have to include those functional dependencies in the closure, and we have to apply Armstrong axiom rules among these functional dependencies, and we can obtain more functional dependencies, some more functional dependencies along with these FDs, given FDs. Okay. So, now let us consider different kinds of examples. How to find the closure? Consider relation. This is the relation which contains some of the columns, and these are the given FDs. Find the closure of attributes and attribute sets. So, what is an attribute here? A, B, C, D. These are attributes. What are attribute sets? A, B, B, C, A, B, C. Combining set of attributes is nothing but attribute set. Simply. Right. So, we need to find out what the closure of attributes and attribute sets. So, let us find the closure of A. The closure of A. A means what here? What is the closure definition? We have to include all the dependencies, right? So, we have to include here whatever the variable that we are going to take, a, comma, and what are the derivations that, or else what are the FDs that a can derive, that we need to include. Okay. So here a we have included. What a derives here? A derives what? BC. A derives BC. So here we have to include BC. Okay. Whether we have to check combinedly these three or these two, any of the two elements derives some more elements. So here AB derives anything? No. BC derives anything? Yes. BC derives what? D comma E. So we have to include D comma E. And again we need to check, whether the set of attributes derives some more attributes. Combination of these attributes derives some more attributes. That means AB derives anything? No. BC derives D, that we have already included. Next, D derives F, D uniquely derives F. So we can include F also. Right. Next, CF derives what? G. So we have to include G. So in this way we have to obtain some more attributes. The closure of A will be like this. We have to include the element itself, and we need to check whether this particular element derives some other elements by considering the given FDs. So let us check that one. See, the same thing. I have included A. Why? Because I am finding out the closure of a particular attribute A. So I have included A. Next, A derives what here? A derives BC by the given axiom, right? By the given FD. A derives BC. So I have included B and C here. I have included B and C. Next, we have to check these three, whether these three combinedly or uniquely they are deriving some more attributes or not in the given FDs. So here BC is deriving DE. So I have included DE. Right. Again, we used to check these set of attributes. So from this D derives F. So we have included F. And next, CF derives G. So here C is there, F is there. So CF can derive G. So we can include these things. So the same thing, in this way we can able to find out the closure of A. Next, let us find out the closure of D. Closure of D. Closure of D means it is represented by D plus. Right. So to find the D plus, here we have to include that element D. We have to check whether this D derives anything. Yes, D derives F. Yes. And we need to again check whether DF derives anything. DF uniquely doesn't derive anything. So we must not include anything, and this is the closure of D. So in this way we can represent the closure of attributes. Attributes means what? A and D. These are single attributes. Now let us discuss the closure, to find the closure of attribute sets. Right. So what is attribute set here? BC, CF. This is nothing but attribute set. Why? Because we have combined two or more attributes here. So what is the closure of BC? BC closure. Let us find out here itself. BC closure. What I have said? BC closure means we have to include these two elements, BC. What derives BC? BC derives D comma E. So we have to include DE. Next, again let us check whether these elements derive some more elements. BC we have completed. D derives what here? D is there. D derives what? F. So we have included F. Right. Next, CF is there. CF derives what? G. So we have included G. Rest of all elements we have already included. Right. BC derives, BD is not there, BE is not there. We have to check only left hand part. Why? Because left hand derives only right hand elements, right? Right side elements. So that is what the thing you need to remember. So this is what the resultant of BC closure. What? BC, DE, FG. Let us check that one. BC, DE, FG. This is what the result. Okay. Next, let us derive for CF, the closure of CF. This is an attribute set. Okay. Closure of CF means what we have to include? We have to include these two elements first, C comma F. Whether C derives anything? No. Uniquely. F derives anything uniquely? No. Combinedly CF derives what? CF derives G. Whether CFG derives anything? No. So this is what the resultant. So CFG. So what we have discussed in this session, we have discussed about Armstrong axioms. Those are nothing but inference rules. So why we have studied these inference rules? Why we are studying? To find the closure. That is nothing but we are finding out some more functional dependencies. How we can able to find out some more different functional dependencies? By considering these Armstrong axioms. So this is what we have discussed, and in the later session let us discuss about normalization. So these are the prerequisites concepts for discussing normalization concepts. So that is the reason we have discussed about FDs first and how to find the closure of a particular sets. Thank you.